Okay, this video is going to go backwards, and this is what we want to end up with. This differential equation, which is Legendre's differential equation. And you notice, even though it deals with the angular theta and phi values, that those aren't there. And one of the reasons is x is standing for cosine theta, and y is standing for the function of theta. So it's just spread out there to be a more general form. And what we won't solve is this stuff. We won't solve where all that stuff comes from, but at least we'll get to this form, and then we'll have more video action to come up with this L times L plus 1 and the m squared and all what those things mean. But they're so important because they give us the molecular shapes, and that's what we want to do eventually. Here's where we left the last video, and what you'll like to know is that all of this stuff is solved for us already, or we're not going to pursue that. All we're going to do is pursue this little thing, which, okay, you say, oh, well, that's pretty simple. Then what is there to solve? It looks like it's already solved. Well, remember, this L is all the spherical portions of the Laplacian, so that's not necessarily that simple. So we'll go to the next screen and see if it starts looking like a challenge to us, which is what we want. We want a challenge, don't we? Well, let me go to the next screen. That looks more like a challenge. There's the 1 over y and sine theta d theta sine theta dy d theta plus sine squared d squared. Okay, we've been working with this already, and we say that this is equal to the separation constant. Well, where did the h bar go? Where did the h bar go? Well, there was an h bar in front of the L, so we just divided out the h bar altogether, so it just brings it right down to the constant. And remember, this constant is one thing that we're going to have to work out, but we'll get there. Just take our time. Remember how we separated the radial from the angular? Now we're going to separate one type of angular from the other. So the angular part is based on the angle phi, which is the rotational angle around the z-axis, and theta, which is the inclination angle to the z-axis. And what we're going to do is break this thing up into two pieces and call it, this y function is now a function of theta and phi, but we're going to break it up into a capital theta. That's supposed to be a capital theta. It's always hard to do that one. And the lowercase theta, which is the variable within that. And then here's the capital phi, which is the function with the variable phi. And we're going to jump right into it. This jumps very quickly, so be careful. Hold on to your hats. This second derivative of, and this would be the phi function, right? Second derivative of phi with respect to lowercase phi is going to be something we want to solve for. And what we're going to try and solve for is this thing right here. Now, where'd that 1 over phi come from for? Well, here's the 1 over y, and that breaks out into 1 over theta and 1 over phi, depending on which variable we happen to be working on. So, now we're going to get into differential equation solutions, and we're going to propose a solution that is equal to negative m squared. We want a solution for phi that will end up giving the second derivative and 1 over phi, and that'll give us m squared. How can we do that? Well, when we're taking differential equations, a really handy thing is the base of the natural logarithm. That exponential is unique in that when you take the derivative of it, you get the derivative right back. You get that function right back plus the derivative times the derivative of what's in the exponent. So let's see if this all works out. Now e to the negative I m phi, so if we take the first derivative of that thing, what do we get? E to the negative I m phi, we got it right back, and then we multiply that times I m. Now why I m? Well, if you take the derivative of phi, you just get 1, right? Right, class? And so what the function, what's left over is the constant, which is I m, or that I is the square root of negative 1, or I squared equals negative 1. Anyway, let's keep moving on here. Then we take the derivative of this derivative. That'd be the second derivative. So then we take that out and we get e to the negative I m phi times, that's just what we had up here. And then we get e to the negative I m phi times that constant again. So it's I m. So what's I times I is negative 1, negative plus negative, or negative times negative is positive, so that gives us a negative 1 and m squared. So that's the solution. If phi is e to the I m phi, and we take it 1 over phi, so that thing drops out and leaves us with m squared. Gulp. Did you follow all that? I just barely did. So let's come down here, and maybe I need to come over here and move the picture up a little bit so we can see everything. So all I did is just plug in the m squared down here. And then here's the constant negative lambda, which figuring out that lambda is going to be a chore, but it'll be a labor of love. All right, we made one change, and that is over here. Notice this had just the lambda on the right-hand side. Well, that lambda is brought over here, and it's got a positive sign because it was negative over here on the last page. Now I'm going to multiply both sides by theta, the function theta. So it gets rid of this 1 over theta that's down here. And let's see what that does. Okay, it puts the theta function out here after this brace. And let's see, 1 over, or bracket, 1 over sine theta. Let's see, what can we do next? Well, here's what's going to happen that is going to be a little bit confusing, but that's what we're here for, is to explain away the confusion. Here's what we're going to do, is simplify the sine thetas by introducing this. An x equals cosine of theta. Now, how can we just throw in an x? Well, here's what we're going to do, is we're going to say that this symbol here, capital theta sub x, is the first derivative of theta with respect to x. So whenever you see that, that's the first derivative with respect to x. So how can we get this sine theta looking like anything? Well, we haven't done the cosine x yet. We'll get there in a little bit. This sine theta here equals, and this is going to take a little thought process for me, is that inside this parentheses is sine theta, first partial of x. Okay, first derivative of x with respect to theta is negative sine. Now, how does that come about? Well, the first derivative of the cosine with respect to theta is negative sine theta. So that's where that sine theta comes from right there. It's all because of that x equals cosine substitution method. So what's going on next? Okay, that was all inside here. So this up here becomes this down here. First derivative of negative sine squared theta times First derivative of theta with respect to x. Wow, how confusing can you be? Okay, derivative of sine squared theta, d theta. Here is the theta, first derivative theta with respect to theta, blah, 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 plus, see, it's a product, so we've got to break it up into two pieces, plus the first derivative of theta x, which is the first derivative of x. So this is going to end up being a second derivative of second order derivative with respect to theta, and then the minus sine squared is out here. Now, what's the derivative of sine squared theta? Let's see. Okay, using the exponent rule, the 2 comes down here and becomes a negative 2 times sine theta times the derivative of sine theta, which is cosine of theta. So all of that became this quantity. Now, everything I say is justified. It's just that you say, why are you doing that? Well, remember our end goal. That's our end goal. So let's see what's happening here. This becomes second derivative of the function theta with respect to x. That's what's listed here. We've got 1 over sine theta, and all of this stuff is supposed to come from what I have up here above. I can refer back to this and feel totally comfortable where it came from. Do you agree? Do you agree how they got that? It's all on this page. So your video proves that you derived it. So we factor out a sine of theta on both of these, and that ends up coming out to be plus sine squared theta, because you've still got that minus sign there. So now let's go to the next page. Sine squared theta, second derivative, minus 2 cosine theta, substitute x for cosine of theta. There's the x, the constant here doesn't change, and there's the 1 minus x squared, and there's the second partial of theta with respect to x. So we have accomplished what we wanted to. How do we get down here? Well, you just pretend that this is y, the function y with respect to x. There you've got it. That double prime there indicates second derivative. Single prime indicates first derivative. And this glob here, this lambda times the theta function is what accounts for, oh, here's the theta function. This is the y. And that constant there is a mess. Is complicated to me, and it might be to you. So where's the justification? That's worth another video if you survived this crazy mess.